Dulong-Pettit model was a classical model where each atom oscillates around the equilibrium position independently from all other atoms. So let's study about the next model, which is called Einstein Model. So Einstein said that the problem is that we think harmonic oscillators as a classical, but this is not true. At atomic scale, we have to use quantum physics. So Einstein model says that we can continue to treat atoms around the equilibrium position as independent from each of the others. So again, each atom oscillates around the equilibrium position with a frequency which is same for all the atoms, that is with Einstein frequency. Now suppose these are two atoms connected by a spring. Of spring constant K and mass M. So we can write the Einstein frequency as omega E, that is angular frequency equal to 2 pi this frequency. So for a classical oscillator, we have mass M and spring constant K, and so what is the frequency of this oscillation? So the frequency of this oscillation is given by omega under root K by M. So in Dulong-Pettit model, energy of the 1D oscillator, 1D harmonic oscillator was represented by in this fashion. So substituting the value of omega, so we can write K is equal to m omega square. Now putting the value of K in this equation, we are going to get the equation as so Einstein said that it is true that each atom oscillates with the frequency omega, which is same for all the atoms. So all the atoms are independent, and since we have translational symmetry in the crystal, all atoms have same potential, same frequency, and same value of spring constant K. So the difference is that, so the main difference is that, sorry, so the main difference is that energy of harmonic oscillator is quantized because quantum harmonic oscillator has quantized energy. So we know that in classical harmonic oscillator, the energy depends on amplitude of the oscillation. So in classical physics, any energy is possible and can change continuously. In quantum physics, the energy of the harmonic oscillator is quantized and is represented by this expression. So this is the case of 1D harmonic oscillator. So it means that let's plot the curve. So this is the curve of half kx square, and it means that we have a potential which has the energy of harmonic oscillator. First of all, it cannot be zero, so the value of n can be 0, 1, 2, etc. So the minimum energy is minimum energy is n equal to 0, that is En equal to 0 plus 1 by 2 h cross omega E, which equates to h cross omega E by 2. Done. So this is the minimum energy level, that is h cross omega E by 2, and these are the other energy levels. So this spacing between the energy level is given by, so this spacing between the energy level is h cross omega E. So basically, if you solve this Schrodinger equation with the potential of half kx square, and we find the stationary states eigenvalues and eigenfunction, then we find the eigenvalue of energy En of this equation, that is n plus 1 by 2 h cross omega E. So this is true whenever we have potential quadratic in displacement. So Einstein said that the energy is given by n h cross omega E, which is equal to here h cross is h by 2 pi and omega is 2 pi ve mu e, sorry, so 2 pi cancel, and we are going to get n h mu e here. So he didn't consider the 0 point energy. So the point is we have to calculate the total energy, that is the internal energy of the system for Einstein. So we have to do the same calculation as before by using this equation, which we have seen in the Dulong-Petit model. So here 3 is the degree of freedom. Na is the number of atoms, that is how many oscillators we have. Number of atoms, that is how many oscillators you have, which is Avogadro number. So because we want to calculate molar specific heat, and here ENT is average value of energy at temperature T. So again, if you increase the temperature, the oscillation energy can be higher. So what is the average value of energy that is quantized? So Einstein says, let's use the Maxwell-Boltzmann equation, but for a quantized system. So in Dulong-Petit model, we have seen that the average energy was given by this expression. That is, this is the phase space, which is the function of position and momentum, multiplied by the probability of the atoms having that energy. That is hxpx by kt dx dot dpx, and we have to also normalize by dividing by this integral. That is minus hx px by kt dot dx dot dpx. So the question is how Einstein calculated the average energy. So the energy now is discrete, so it is not an integral. So the answer is, energy is now discrete, not continuous. So we must sum over. So we must sum instead of doing integration, instead of using integral. So the expression becomes something like this. So the expression becomes something like this. The average energy is given by this summation over n here nh mu e divided by the probability of finding that energy state by kt divided by n minus nh ve by kt. So this is normalized. So the above equation is this equation is very similar to the Planck's calculation. So this equation is very similar to the Planck's calculation. So the Planck made the hypothesis that the energy of electromagnetic field is quantized, and calculated the average energy of electromagnetic wave in a cavity using the above equation, which could solve the problem of black body radiation. So in 1D quantum harmonic oscillator, the energy is represented by in this fashion. Let me rewrite. Summation over n multiplied by the probability and we have to normalize it. And after further simplifying, we are going to get similar in this fashion. So the interpretation we can write. So the above interpretation we can write in this way. Okay, wait a minute. So we can write this above interpretation in this fashion. Okay. Multiplied by h mu e. So here this quantity is 1 by e power h mu e by kt minus 1. So this n can be interpreted as this is the number of vibrational quanta, that we have in an oscillator. Okay, so we can say that we can say this expression in two ways. The first way is that the system is in n energy quanta in the system, and the other way of saying is that we have n energy quanta in the system. Okay, so we can say that this is the average number of vibrational quanta at a given temperature. So it gives us the statistics of vibrational quanta at any temperature. So what is the name of the statistical distribution for vibrational quanta? We call it as Bose-Einstein statistics. So it means that we have many atoms, that is many oscillators. So one will have the energy indicated by the 1 minute. Let me plot the graph again. Okay. So it means that we have many atoms and many oscillators, and one will have the energies indicated by these green lines. The spacing between the green line is given by h cross omega, and the minimum energy is h cross omega by 2, as we already seen. So the average value of vibrational quanta is given by this expression. Sorry, h mu e by kt minus 1. So if you increase the temperature in average, the energy will increase. Now let's substitute the expression of the average energy in this expression, that is in this expression. So after substituting the value of average energy in this expression, we are going to get taking the derivative of this thing, that is we are going to get the expression somewhat like this: 3n Avogadro number kt square h cross omega e square h cross omega kt divided by e h cross omega e by kt minus 1 square. So this is the specific heat obtained by the Einstein model. See, the only difference with the Dulong-Petit model is that the harmonic oscillator has quantized energy instead of being continuous. So now let's plot the obtained results. Now let's compare the results obtained by the Dulong-Petit model and Einstein model. So okay. So this was the curve obtained by Dulong-Petit model. And now the curve obtained by the Einstein model looks something like this. So the temperature, let me plot this in a good manner. Yeah, so this point where the both curves are equal is the Einstein temperature. This is T cube curve, and here they are equal, and this is the e power minus, sorry, this is not minus, kt. Okay, so at the higher temperature, that is for t tending towards infinity, um, specific heat is closer to 3R, that is 3 kNa. And for smaller temperature, this is minus. For small temperature, CV specific heat is tending towards kT. So we can say that at lower temperature, the Einstein model underestimates the real value of specific heat. So the temperature at which the behavior is similar is called Einstein temperature, and it's calculated by this thing, k dot Te equal to h cross omega e. So the Einstein temperature is given by Te h cross omega e by k. So we can see that specific heat is not constant. It goes from 0 to 3R. This is 3R, the constant value. And shape is similar to the real one. But the problem is that in Einstein model, it goes to 0 very fast. So what is wrong in Einstein model? So Einstein was wrong to assume that all the atoms have same frequency and are independent. Independent means suppose you have many atoms, then one atom can vibrate. Suppose you have many atoms. Suppose you have many atoms, and one atom can vibrate, and all other atoms are stopped. So independent means vibration of one atom doesn't affect other atoms. So we have an independent quantum oscillators, which is not true. Obviously, it's not true. So if you move the one atom from its initial position, then the potential for all other atoms will change. So physically, the potential is the column interaction between the ions, and if the atoms are displaced or vibrate, then the neighboring atoms can start to vibrate. So basically, we can infer that all the atoms are connected. So the question is, how can we describe in a simple way the harmonic potential where all other atoms interact with each other? So we can visualize by this fashion that all other atoms are connected to each other by a spring in this fashion. So this is just a way of representing. So it's like connecting all the atoms with a spring. It's like having spring between all the atoms and others. So each atom movement has influence on all other atoms. So this potential is an electrostatic potential. So we will consider the spring between the nearest atoms. Important point to understand is that the model with independent atom is not correct, and all atoms have same frequency, which is not correct. So the good model for specific heat is given by the Debye model, which we'll be studying in the upcoming lectures. So this is the best model for specific heat, Debye model. And now let's understand the physical interpretation of the Einstein specific heat. So why is so why why is CV is that the specific heat is 0 and then goes to some value, that is the classical value. So basically what happens is that we have quantum oscillators, and imagine the graph is no now imagine this graph of the quantum oscillators in this fashion. This is the energy levels. This is the energy level, and the average energy of quantum oscillator is, we know that is kT. So let's start plotting. This is zero energy level. This is keeps on increasing. In standard fashion. So this is 0. This is h cross omega by 2. This is n equal to 1, n equal to 2, n equal to 3. So if the average energy of the quantum oscillator, that is the average energy of quantum oscillator, is very less than the quantum energy, so the system at 0 Kelvin has the lowest level, that is ground level. So we need h cross omega, that is quantum of energy, to go to the first level. So if the temperature is so small, then the average thermal energy is not enough to excite the vibration. So at lower temperature, the oscillators are frozen. So if we increase the temperature, the system will not get energy because there is not enough energy for moving from one level to other. So below the Einstein temperature, when the average energy of the quantum oscillator is same to the quantum energy, then the system starts to unfreeze. So when the temperature is the Einstein temperature, that is T equal to TE, after the Einstein temperature, thermal energy is enough to execute the oscillator, and the system starts to behave as a classical system. So below the thermal Einstein temperature, the energy is not enough. Of course, the specific heat is not 0 because we have a statistical distribution. So the physical interpretation is that at low temperature, the thermal energy is not enough to excite the vibrational levels or vibrational quanta. So the system is like frozen system and cannot get energy. So the specific heat is small. Then it increases at room temperature. Basically, the spring is much less than the average energy of the quantum oscillator. So this is very important because in the correct model, these all things will remain valid. The only difference is that we don't have each atom as an independent oscillator, but all the atoms oscillate together and have different frequencies of vibration. So what we need to see is how to describe the vibration of atoms, which we will going to study in next lecture. and which are all connected. So the atoms vibrate together. That is, we have collective vibration of the atoms. So in the next lecture, we will study about the adiabatic principles to describe the vibration of these atoms. So for now, thank you.